Modern vehicles are rolling computer networks. They are physical machines governed by millions of lines of code. That digital architecture carries a brutal physical reality. If an attacker breaches a vehicle's network, they aren't extracting credit card numbers. They can remotely hijack the steering, disable the brakes, or trigger the airbags at 60 miles per hour. To address this threat, the United Nations established an international mandate known as ISO21434. It makes airtight cybersecurity a strict legal prerequisite for selling any new vehicle. On paper, the solution sounds obvious. You apply the exact same firewalls, passwords, and encryption protocols used to secure banking servers and smartphones. But banking servers sit in quiet, climate-controlled rooms. A car is heavy machinery that violently vibrates over potholes, bakes at 125 degrees in the desert, freezes in sub-zero winters, and requires control signals to process in fractions of a millisecond. Standard IT security would crush the system entirely. Securing a vehicle poses a severe engineering paradox. You have to build digital defenses that do not accidentally sabotage the machine's ability to survive the physical world. Let's start with the hardware. A common attack involves opening a control module and physically prying the microchip off of the circuit board to extract its cryptographic keys in a lab. The standard defense is aggressive. Engineers glue the chip to the board using a high-strength epoxy resin. If an attacker tries to remove it, the silicon splinters into useless pieces. But high-performance cryptographic processors performing continuous data encryption generate intense bursts of heat. Look at this cross-section of a microchip. When that heat spikes, the epoxy, the fiberglass board, and the silicon chip all expand at completely different rates. The expanding resin pulls the chip's corners upward, snapping the solder joints. To survive, finite element simulations dictate stripping heavy glue, applying precision epoxy dots to exact anchor points. Then they drill microscopic holes called thermal vias directly into the board beneath the chip, creating a physical escape hatch that bleeds the excess heat away from the processor. A digital vault is useless if its own defense mechanisms melt the physical assets inside. The conflict worsens on the vehicle's internal communications network. An attacker who gains access can inject fake messages telling the anti-lock braking system to shut down. To prevent this, regulations require every single command to be authenticated with heavy cryptographic passwords to prove it came from a legitimate component. But generating true random numbers for those passwords takes time. If the system has to pause and harvest enough raw entropy to create a secure key, your brake signal is delayed by precious milliseconds. This diagram shows another physical bottleneck. The wires of a standard automotive network have a strict size limit of just 8 bytes per message. A standard 16-block encrypted password is double that size. It literally will not fit. To solve the speed problem, hardware harvests random numbers while parked, feeding a deterministic algorithm that fires keys instantly. To fix the size limit, passwords are ruthlessly chopped. A fragment rides with the brake command, and the receiving computer drops messages failing verification. Engineers intentionally sacrifice absolute cryptographic strength to guarantee the split-second physical reaction time needed to prevent a crash. Even software updates pose a massive risk. Hackers often attempt downgrade attacks, intercepting an over-the-air update and forcing the car to install an older, vulnerable version of its software. The ultimate defense against this is physical, a microscopic circuit called an eFuse. When a secure update finishes successfully, the processor runs a charge through this tiny wire and permanently burns it in half. That burned fuse is an irreversible hardware stamp. The car's boot sequence checks the fuse upon startup and instantly refuses to load any software older than that exact physical state. But look at this logic flow. Imagine a legitimate, brand new software update corrupts overnight in your garage. The system detects an error and tries rebooting from backup software. But the burned eFuse assumes a downgrade attack and slams a barrier down. Permanently paralyzed by its security, the vehicle is a hard brick, requiring expensive hardware replacement to fix a single file. To avoid this catastrophe, manufacturers embed a golden image, a bare-bones, unerasable operating system burned deep into the silicon at the factory. It provides a highly restricted physical backdoor, allowing a mechanic to plug directly into the dead system and resurrect it. Defeating digital threats requires permanent physical hardware anchors, but it also requires the foresight to engineer an escape hatch for when those anchors drag the system under. Automotive cybersecurity is an illusion if it is treated purely as code floating in a vacuum. It requires an intense collaboration of disciplines. Cryptographers writing encryption algorithms must sit at the exact same table as mechanical engineers designing thermal vents and compliance officers tracking UN regulations. Every time a driver presses the brake pedal, they are relying on a meticulously calculated compromise, a delicate balance between locking hackers out of the network and keeping the driver alive in the physical world.